Hello students, today we will discuss about spectrofluorimetry. Let's have a brief introduction. Spectrofluorimetry, as the name suggests, takes the advantage of the fluorescent properties. It is primarily concerned with electronic and vibrational states. So, before understanding about spectrofluorimetry, it is necessary to know what is fluorescence. The term fluorescence comes from the mineral fluorspar, calcium fluoride, when Sir George G. Stokes observed in 1852 that fluorspar would give off light, that is, fluoresce, when exposed to electromagnetic radiation in the ultraviolet wavelength. So, fluorescence is an emission phenomenon of a molecule where radiation is emitted when energy transition occurs from higher to lower state. There are two types of fluorescence: extrinsic fluorescence, which are emitted by the non-fluorescent compound coupled with the fluorescent probe, and the intrinsic fluorescent compound, where the native compound exhibits the property due to the presence of aromatic groups. This technique is very useful in determination of organic and inorganic substances, determination of uranium salts in nuclear research, and determination of vitamins. So let's come to the principle. As we have learned in the chemistry, when an atom or molecule absorbs radiation, the energy of the photon absorbed excites an electron to a higher orbital. Now, the electron needs to come down back to its ground state. It can do so in two different ways. In one way, the electron can directly return to its ground state in a single step, where it will emit radiation of the same wavelength that it has absorbed. In another case, the electron can do so in stepwise manner through intermediate energy levels, and in this process, it will obviously emit quanta of radiation to its energy step. Since each quantum will have a smaller amount of energy, the radiation emitted will have a longer wavelength than the original exciting radiation, since we know that energy is indirectly proportional to wavelength. If this happens, then the emitted light will have many different wavelengths, which will correspond to each of the intermediate level, which the electron will add up on its way back to the ground state. Thus, fluorescence spectra are band spectra, and they are independent of the wavelength of the radiation absorbed. Now, theory. Fluorimetry can be used as a tool for the determination of very small concentration of substances which exhibit fluorescence. Here, we can also apply the Beer-Lambert's law, that is A equal to log I naught by IT equal to ACL, where A equal to absorptivity or extinction coefficient of the absorbing material at wavelength lambda, C is the concentration of the substance, L is the path length, and I naught and IT represents the values of intensities of the incident radiant energy and transmitted energy respectively. The intensity of the radiation absorbed can thus be given by I naught minus IT. The intensity of the fluorescence F is given by F equal to I naught minus IT into phi, where phi is the quantum yield of the fluorescence, and it is defined as the ratio of number of photons emitted to the number of photons absorbed. At very low absorbance, less than 0.02, the equation will be F equal to 2.3 into I naught into A into C into L. Instruments that measure the intensity of fluorescence are called fluorimeter. There are two general types of instrument used in spectrofluorimetry. Number 1, filter fluorimeter, which uses filters to isolate the incident light and fluorescent light. Number 2 is the spectrofluorimeters, which uses diffraction grating monochromators to isolate incident light and fluorescent light. Now let's discuss about spectrofluorimeters. Spectrofluorimeters measures the fluorescence intensity at variable wavelengths of excitation and emission and are able to produce fluorescence spectra. Fluorescence may be expected generally in aromatic molecules that contain conjugated double bonds, polycyclic aromatic compounds with great number of pi electrons. Substituent also has strong effect on the fluorescence. Substituents such as NH2, NHCH3, NCH3, OH and OCH3 groups enhance the fluorescence, while electron withdrawing groups such as NO2, chlorine, bromine, iodine and COOH group decrease the fluorescence. Rigid molecules are strongly fluorescent such as fluorescein and eosin, while non-rigid molecules such as phenolphthalein is not fluorescent, and formation of metal chelate promotes the fluorescence. Let us see what are the components present in the spectrofluorimeter. It mainly comprises of number 1, a continuous source of radiant energy, mercury lamp or xenon arc or tungsten lamp. Number 2, two monochromator system. First monochromator, usually a prism P1, to choose the wavelength with which the sample is to be irradiated. A second monochromator P2, which placed after the sample, enables the determination of fluorescent spectrum of the sample. Number 3, sample cell. Sample cells are cylindrical or polyhedral made up of color-corrected fused glass and path length normally 10 mm to 1 cm. The sample holder has a device to maintain the temperature as the fluorescence is maximum between 25 degrees Celsius to 30 degrees Celsius. Number 4 is the detector, which is usually a photomultiplier or photovoltaic cell or phototubes suited for wavelengths greater than 500 nanometer, and lastly an amplifier. Now let's come to the instrumentation. Two monochromators that are employed have its own different purposes. The first one is used for tuning the wavelength of the exciting beam, and a second one for analysis of the fluorescence emission. Due to the emitted light always having a lower energy than the exciting light, the wavelength of the excitation monochromator is set at a lower wavelength than the emission monochromator. The detector is usually a sensitive photocell. The better fluorescence spectrofluorimeters in laboratories have a photon counting detector yielding very high sensitivity. Temperature control is required for accurate work as the emission intensity of a fluorophore is dependent on the temperature of the solution. The radiation source is generally either a mercury lamp or a xenon arc. Excitation wavelengths are frequently selected in the ultraviolet region and the emission wavelength in the visual region. There are two approaches for the illumination of this sample: the basic 90-degree illumination and the front face illumination. Now let's come to the factors affecting fluorescence. Number 1 factor is the concentration. The previous equation shows that the fluorescence intensity of a substance is proportionally to concentration only when the absorbance in a 1 cm cell is less than 0.02. With increasing the absorbance introduced an increasingly significant error. that is the inner filter effect, and cause negative curvature in calibration graphs. If the concentration of the fluorescent substance is so great that all incident radiation is absorbed, the equation will be F equal to I naught. That is, the fluorescence is independent of concentration and proportional to the intensity of incident radiation only, a property that may be utilized to determine the approximate emission characteristics of a light source. Number 2 factor is the intensity of light. The intensity of exciting light is proportional to both the intensity of exciting light and the concentration of the fluorescing material at low concentration, that is 10 to the power minus 4 to 10 to the power minus 7 m, and within narrow limits. Number 3 factor is the substituents. Substituents strongly affect fluorescence. A substituent that delocalizes the electrons such as NH2OH, F, OCH3, NHCH3 and NCH3 two groups often enhance the fluorescence because they tend to increase the transition probability between the lowest excited singlet state and the ground state. Electron withdrawing groups containing chlorine, bromine, iodine, NHCOCH3, NO2 or COOH decrease or quench completely the fluorescence. Next, fourth factor is the molecular rigidity. Fluorescence is particularly favored in molecules that possess rigid structures. Molecular rigidity lessens the possibility of computing non-radiative transitions by decreasing vibrations. This minimizes inter-system crossing to the triplet state and collisional heat degradation. For example, fluorescein and eosine are strongly fluorescent, but a similar compound, phenolphthalein, which is non-rigid and where the conjugate system is disrupted, is not fluorescent. Factor number 5, polarity of the solvent. The polarity of the solvent also affects the fluorescence and phosphorescence. Solvents containing heavy atoms or other such atoms in their structure decrease the fluorescence. Number 6 factor is the quenching. Quenching is the reduction in the intensity of fluorescence due to specific effect of constituents to the solution itself. Quenching may be caused in several ways. For example, concentration quenching may be caused by excessive absorption of either primary or fluorescent radiation by the solution. This is also called the inner filter effect. If this effect occurs as a result of absorption by the fluorescent substance itself, the phenomenon is called self-quenching. Number 7 factor is the presence of dissolved oxygen. The presence of dissolved oxygen often reduces the emission intensity of a fluorescent solution, probably due to photochemically induced oxidation of the fluorescent material. Quenching also occurs as a result of paramagnetic properties of molecular oxygen. Anthracene is well known to be susceptible to the presence of oxygen. Factor number 8, changes in pH. pH also exhibits a marked effect on the fluorescence of compounds. For example, aniline shows a blue fluorescence in the range of pH 5 to 13 when excited at 290 nanometer. At lower pH, aniline exists as the aniline cation and in highly alkaline media as the anion. Neither anion nor cation is fluorescent. Fluorescence is more commonly associated with pi-pi states than with n-pi states because pi-pi states possess shorter average lifetime and because deactivation processes that complete with fluorescence are much less likely to take place. Number 9 factor is the temperature and viscosity. Variation in temperature and viscosity will cause variations in the frequency of collisions between molecules. Thus, an increase in the temperature or the decrease in the viscosity is likely to decrease the fluorescence by deactivation of the excited molecules by collision. Similarly, many substances are not normally fluorescent at room temperature, are capable of emitting light when excited at low temperature or when in a viscous solvent or glassy matrix. The temperature coefficient of fluorescence is typically 1% degree Celsius increase in the temperature. Number 10 factor is the photodecomposition. Spectrofluorimetry requires high intensity illumination for irradiation and the risk of photochemical change is thereby increased. An error up to 20% could quite easily arise. It may be possible in unfavorable cases to select radiation of a wavelength which is not strongly absorbed so that the extent of photochemical change is reduced. At the same time, adequate sensitivity is retained. So now, let's see the advantages of spectrofluorimetry. Number 1, it is more sensitive when compared to other absorption techniques that could determine concentration as low as microgram per ml or nanogram per ml. Number 2, they can also easily achieve precision up to 1%. Number 3, it is also more specific than the other absorption method because it has characteristics of both excitation and emission wavelength. Now, let's look to the applications of spectrofluorimetry. Application of the technique is very varied, despite the fact that relatively few compounds exhibit the phenomenon. A compound may have its fluorescence and absorption spectra compare as an aid to the identification. The effect of pH, solvent composition, and the polarization of the fluorescence may all contribute to structural elucidation. The major application of fluorimetry in biochemistry is in quantitative determination of materials present in low concentration. Acids of vitamin B1 in foodstuffs, NADH, alcohols, hormones, drugs, pesticides, carcinogens, chlorophyll, cholesterol, porphyrins, and some metal ions indicate the range. It also can be used to differentiate between self and contaminant quenching by adding a known quantity of standard to an unknown quantity of a pure compound and measuring the fluorescence before and after the addition. So finally concluding, we have the method is less tedious and less cumbersome as compared to other methods which require long run time and suffer from prolonged operation procedures. Moreover, the sensitivity offered by this method is far higher than other absorption methods. The compounds can be analyzed up to the levels of nanograms. Hence, high sensitivity and specificity are real advantage of this method. Further, quantitative estimation is possible which can easily measure the amount of the analyte in the mixture. That's all. Thank you.